Okay. So I think we have covered this stress and strain, and we have seen the bars in series combination, right? We have seen bars in series, right? We have to see the composite structure or compound structure. Now, before discussing this thing, we'll discuss one more important point. Just wait. One important concept, we have to cover in that series combination only. When the bars are connected in series, there we have to cover, one important thing. Try to understand. Again, I'm just repeating the same thing, but there is something else. Do not worry, we are not going to discuss about the deformation and the stress calculation. We are going to see something else. So bars in series combination. Bars in series, right? When they are connected in series, then what will happen? That is what we need to see. Now try to understand the things. Bars in series. So yeah, I'm giving you one loading condition, and the different the bars will be given to you. Suppose a bar is there which is made up of so many sections, or you can say that definitely we have the different types of beams made up of different types of beams, which is having the same cross sectional area. Although we have the same cross sectional area, and now the loading diagram I will show you. Very important. Please pay attention. If you know something about this, just leave apart from this, right? Just leave aside and try to listen each and everything very carefully. P. Now this is a cantilever beam, right? A beam which is fixed at one end, right? Yes or no, guys? And the length we can say L length of all the basically sections. So either you say 3 bars or you say 1 bar which is made up of 3 sections. Are you getting my point? Yes or no, guys? This is section 1, section 2, section 3. Understanding or not? And is it clear the loading conditions? Is it clear the loading conditions? Tell me, guys. Please try to respond as quickly as possible so that we can cover maximum thing in the class itself. If you just delay in replying, so that I may miss some content also. Now, so here the loading condition is being given. You know that whenever we have the cantilever beam, there is a reaction forces will be coming. That reaction forces, suppose that I'm assuming like this. That reaction forces, I'm assuming horizontal reaction will be coming. There is a right vertical reaction will be coming, and there is movement will also be coming. But movement and vertical reaction will be zero because static equilibrium conditions. By how to calculate the reaction forces, where RH is nothing but reaction forces. Reaction forces by static equilibrium conditions. By static equilibrium conditions, what we can do? By static equilibrium conditions, summation of forces along x direction must be zero. Summation of forces along x direction must be zero. Any sign convention you can follow. Any sign convention you can follow. So it's up to you. Whatever the sign convention I told you for the member to be called tensile member or compressive member, that is different. All of you are understanding my point, what I'm saying? Please check it out. All of you, please check it out. The difference between the sign convention for static equilibrium conditions and for other what I have discussed, that is about tensile and compressive, that is different. Suppose that I'm assuming that in this direction I'm assuming this to be positive. Suppose my sign convention as of now at this moment right hand side, if right side, suppose anything which is acting in the positive x-axis, I'm taking it to be what? I'm taking it to be positive one. Then what we can have? Plus 2p plus 3p minus 8p minus RH must be equal to 0. From here, just tell me the value of RH. From here, just tell me the value of RH. Minus 3p or not? Minus 3p or not? That means whatever the direction we have assumed of the reaction forces, that is incorrect. What should be the direction? What should be the direction? Tell me, guys. What should be the direction? Something like this or not? What should be the direction? Something like this or not? Please check it out. Please tell me, guys. Are you understanding or not? No, just wait. Actually, there is a, RH will be, suppose why I have considered minus sign, because that is acting in the negative side, negative directions, right? That is what acting in the negative directions. So from there we got RH value to be what? Suppose it is coming to be what? Suppose it is coming to be positive. Then what would have been the directions? Plus x-axis or minus x-axis? Suppose RH value, whatever initially we have assumed in this direction, right? And suppose RH value is coming out to be positive. Suppose RH value is coming out to be positive. Then what would have been the direction of RH? Negative x-axis or positive x-axis? Tell me, guys. Yes or no? Hello? I think there are a lot of confusions are there. A lot of confusions are there. See, try to understand the subject and sign convention. Especially if I talk about the SOM will play around the sign convention only. The SOM will play around the sign convention only. Suppose that, my dear friend, I have assumed my sign convention this to be positive. Suppose that means whatever the forces that is acting in the positive x-axis, that is positive, and whatever acting in the negative direction, that will be negative. Plus 2p because it is acting in the positive x-axis, plus 3p because that is acting in the positive x-axis, minus 8p because it is acting in the negative, minus RH because it is acting in the what? Negative. If suppose RH is coming out to be positive value plus 3p, then the direction would have been this one only. Understanding what I'm saying? Understanding what I'm saying? We have assumed the direction. See, even in the starting, we have not calculated any reaction forces. We just assume the direction to be what? Something like this. Like this. Suppose we got RH value to be positive, then we have whatever the direction we have assumed, that is correct one. But right now, my dear friend, it's coming out to be negative. That means RH is not acting in the leftward direction. RH will be acting in the rightward directions. Understanding or not? These are the very small thing, very silly thing, but you do mistake in the gate examination based on this only. Believe me. Now, so you got the RH direction also. You got the RH direction also. Now, my dear friend, what else we have to calculate? I just want to know the question. What is the question? What is the axial loading diagram? What is the axial loading diagram for this particular question? You have seen shear force diagram. You have seen the bending moment diagram. Anywhere before you have seen the axial loading diagram? Axial loading diagram for above case. Axial loading diagram for the above case. Tell me, guys, what will be the axial loading diagram for the above case? Now, let me just draw the options based on the options. It might be clear. Try to see. How many of you know the bending moment diagram and shear force diagram? How many of you know about the bending moment diagram and shear force diagram? How many of you know about the bending moment diagram and shear force diagram? None of the above. Which option is correct? This is my zero reference. This is my zero reference. From there only we are calculating the values. From there only we are calculating the values. Very important thing, guys, that we are discussing right now. Till now, this particular part has been untouched in GATE examination. Till now, they have not asked this question, right? So at any point of time, they can touch this particular question, right? It's a very important. Try to understand. I will give the solution also. Do not worry. Sir, we have been calculated in the last class in the section wise, A, B section, BC section, CD section. We have calculated section wise. Am I right? We have calculated section wise. A, B, C, D. Am I right or wrong? We have calculated section wise. But sir, we never come across at the particular point what should be the value of the load. Because if you see the diagram, it is a point wise. It is a point wise. It is a point wise. At the particular point, at that particular section, what will be the loading diagram? They are asking. Not in the member sections. Not in the member sections. So it's a very simple question, my different. Let's see the solution. So let me draw the once again. This is A, B, C, D. The loading diagram will be 2P, 3P, 8P, my different. And of course, the reaction forces I am calculating as to be 3P. 3P. Now, in the member AB, what is the force in the member AB? Any one of you? What is the force in the member AB? Now you try to follow the sign convention which I told you. What is the sign convention? At any member, whenever the forces are like this, negative force. Well, any member, the forces are something like this, it's a positive one. Try to follow this sign convention. Forget about the sign convention that I told you for summation of forces in the x direction, that is equal to what? 0. Tell me, guys. What will be the forces in the member AB? Again, let me just denote it by minus 3P. Force in the member BC plus 8P minus 3P plus 5P. What is the force in the member CD? Either you calculate from the right hand side or you just calculate from the left hand side. The value must be same, plus 2P. Now do not say, sir, whatever the sign convention you just said, in this direction it should be positive, summation of forces along x direction must be 0. This sign convention, where it is, do not follow. Follow this one. For this one, for individual member calculations, you try to follow this particular loading diagram, right? Now my different. You got the force in the individual member. Now I'm asking you, what will be the force at the point A? What is the force at the point A? What is the force in the particular point A? See, in AB member, the force is what? 3P compressive. 3P compressive, you know that. So what should be the value of the force in AB? 3P minus 3P. Then what is the force in at the particular point A? Minus 3P only, right? See, there's no other force apart from this 3P force. But there is a very, very important section. Very, very important. What is the force at the point B? My question is, what is the force at the point B? the larger of FAB and FBC. My dear friend, B point is coming here also, B point coming is here also. So it will take the maximum value among AB and BC, not 8P, not 8P, my dear friend, not 8P. 8P effect will cancel out from the left hand side support, that is 3P, right? Then what should be the value of the larger one? 3P or 5P? 5P. That will be the value. What is the force at C? What is the force at C? What is the force at C? C again is coming from what? Both the particular FCD and FBC. Then whatever the larger value is there, that is what we are going to take it out. 5P. Larger value. The larger of FBC and FCD. Now some of you might be thinking, so what the hell you are talking about? I'm talking absolutely correct. My different C point, you might be looking at, let me draw the points. Suppose point C, you just look it like 3P force is acting. Some of you might be thinking, sir, 3P force is acting. But see, C is a part of the BC member, C is the part of the CD member. It is an intermediate connection point. Now, if you just want to design the material just on the basis of point C, you will design on the basis of lower load or higher load. You will design for the worst condition or best condition. If you design for the best condition, my dear friend, for the least amount of load, in actual condition, if suppose larger amount of load will be acting, your material will fail. This type of discussion will happen in the machine design. Understanding what I'm talking about? Tell me, guys. What is the force in the point D? Exactly, force D. At the point D, there is no other force. D is a part of the member CD only. D is a point which is a part of the CD member. And in the CD member, there's only one force, that is 2P. Why we are calculating two times in at the point B and point C? Point B is a part of FAB, that is AB section, and point B is a part of the BC section. Among all sections, whichever the maximum is there, that is what we have to consider. Now, my dear friend, you can comfortably draw the diagram. That is my challenge. Now, look at the diagram very carefully. Look at the diagram very carefully. At point A, the load is what? In the negative directions. At point B, let me first of all put the points. Put the points. Point A, 3P downward. 3P, that is also constant. Suddenly, at the point B, what is the value? What is the value? 5P, right? 3P already there, but again it is moving toward 5P in the positive direction. So it's a 3P minus 3P. Now it is jumping to what? Plus 5P. Again, that will be constant because there is no other force in between the section B, C, my dear friend. Suddenly at the C, it's a constant 5P. This particular thing is what? Constant 5C. But suddenly what is happening? Suddenly what is happening? At the point D. At the point D, what is the load value? Plus 2P or minus 2P? Plus 2P or minus 2P? Now, you can draw the free body diagram. Yeah, correct. Now, if you draw the free body diagram of AB member, or where we can draw FC part alone, I will tell you. Do not worry. I will tell you. So again, it is coming out to be same. 2P. Now it is being closed like this. Now, some of you might be confused. So point B and point C, a lot of confusions are there. Can you please clarify? Now let me clarify this thing. 3P. What will be the free body diagram of BC member? What will be the free body diagram for BC member? What will be the free body diagram for BC member? What will be the diagram for CD member? Pay your attention very, very carefully. Pay your attention very carefully. Section B, Section C. Section B, Section C. Pay your attention very carefully. Pay your attention very carefully. At the point B, how many types of loading condition you might have seen? Minus 3p, that is also acting, plus 5p, that is also acting. At point C, what is happening? Plus 5p and plus 2p, both are acting. Plus 5p plus 2p, both are acting. Check it out. Please check it out. This thing will more clarified when we see the shear force diagram and bending moment diagram. This thing will more clarify when we see the shear force diagram and bending moment diagram. Right? That means in a very simple, in short, what I can say, try to understand. Force at A, only one direction is there. From here to here, it's a -1. If it is also -1. If I just move from here to here, like this, whenever I find something like this arrow, I will put negative. So minus 3p. Force at B will be what? Force at B will be what? Again minus 3p only, but again 2-time calculation will be there. Minus 3p, but again there is a at point B there is a one more force is acting in the what? Leftward direction. I told you if I just move from here to here like this, and if I found something like this negative arrow, that if I found the arrow something like this, I will put negative. If I find something like this, I will put positive. Plus 8p, 5. And that is what my showing it's showing my different. If somebody will ask you, if somebody will give the loading diagram, this is what axial loading diagram. This is what you have, the axial loading diagram. If somebody will give you the axial loading diagram and he will ask you the bar loading structure, simply if he'll ask you, represent it, then what he will say? At the point B, how many total load is acting? How much amount of load is acting? 5p minus and minus 3p, 8p load. You can check it out. If somebody will ask you what is the at point C, how many types of total load is acting? Plus 5p, in that minus 2p. That is what we have, 3p. That is what we have, what? 8p. Check it out. Whatever the vertical lines are there, that represent the magnitude of the load that is acting at that point. Vertical line shows the magnitude of the load at that point. Is it clear? All of you? Check it out. And at the end, your diagram must be closed. At the end, your diagram must be closed. It's starting from 0. It must be ended from, at the end, what? 0 only. Why it has to be ended with a 0? Because to maintain the static equilibrium condition of the body, right? So these are the small things that will be very useful, my dear friend, for the development of this particular subject. Done, all of you? Is it done? All of you have noted down? Now, note down the stresses in the bars of the composite member. When we have the composite structure, or we can say that the stresses in the bars of compound members. Two members which is being connected inside the other member, that is a compound member. Simply we say parallel connection. Before section, what we have covered is a series connection. Right now we are discussing the parallel connections. Very, very important. Note it down. The parallel connections. Note on the diagrams. Done. Correct. Now, note on the two conditions. That is what we have seen the condition in the series combination. Here we have the conditions. Here when the bars are connected in composite way, or suppose one member is being connected inside the other member, right? Something like this. This is the one member, and outer one is what? Other member. Second member is being connected inside that one. So in this condition, what will happen? P will be equal to what? P1 plus P2. So whatever the member will be there, they do not carry the equal amount of load. The load will be shared. The load will be shared, my dear friend. And load will be what? Shared in such a way that the external load can be supported. Whenever heavy structure is being is to be supported externally, then we use bars in compound members, or bars in what? Parallel combination, rather than bars in series combinations. In series combination, what will happen? The load will be carried out equally if there is only external load without any intermediate forces, right? But here what will happen? Whatever the deflection will be there because of this loading, the deflection in both the member will be same. Deflection in one and deflection in two will be same. This is the first equation, and this is going to be second equation, my dear friend. That is a very, very important. Please note down. First equation, and this is going to be second equation. Done, all of you? Perfect. We'll see the numerical, do not worry. Note down stresses and strain in statically indeterminate structures. I told you about the indeterminate structure, right? Which structure or beam is called as indeterminate structure, right? In the engineering mechanics, can you please check it out? Whether we have seen or not. Perfect. Perfect. Now, please note it down, the topic, then we can discuss the this particular concept with the diagrams. I think done, right? Perfect. Now, not only the question we will solve for this particular section, for this particular concept, directly I have taken the question and we will try to solve the question actually. So, yeah, in fact, I can see, just wait, I can see whether there is a question or not on the basis of this. I think no, there is no question. Yeah, note down. Note down, please, this particular section. So there is a fixed member. There is a fixed member, not from only from one side. Both the sides are there. Both the sides. That means any bar which is being fixed at both the ends. What will be the total deformation? Only being fixed at one end, there is a deformation. There is no doubt. That is PL divided by A. But when it is fixed at both the ends, then what will happen? Zero. 0. Now try to remember this particular concept. That will be useful. Try to remember this particular concept, and this concept will be useful. Do not worry. This concept will be useful. Now, my different section AB, BC, CD. So I'll be drawing. I will not be drawing once again. Reaction forces I'm taking like this: RAH and RAD. I'm just taking my convenient direction in the left side. That's it. First of all, we need to calculate the reaction forces. Yes or no, guys? To calculate the forces in individual member AB, BC, CD, all of you can hear me? All of you can hear me? Perfect. Suppose that, my dear friend, I need to calculate the forces in AB member, BC member, CD member. I need to calculate the reaction forces. And how we can able to calculate? Summation of horizontal forces in x direction must be 0. Sir, what is this? Sir, this is a static equilibrium conditions. Static equilibrium conditions. This is my static equilibrium condition, my dear friend. Right? Summation of forces along x direction must be equal to 0. Now, further what I'm doing, I'm assuming the direction to be what? In this direction to be positive. So whatever the forces that is acting in the positive directions, you take it positive. Plus 200 plus 125 minus RAH minus RAD, that is equal to 0. Then what about RAH plus RAD? Can I say 325? Can I say 325 kilonewton? Check it out. Perfect. Perfect. My dear friend, what will be the forces? This is the first equation. This is my first equation. Now tell me, guys, we have only one static equilibrium equation, right? Some of you might be thinking, sir, what about the summation of Fy0? Do not use it because we don't require, there is no vertical force. There's no vertical load, so there will not be any movement also. So this two will not be useful, but the usefulness will be there for this one. That means one is static equilibrium equations, one is static equilibrium equations. How many unknowns? How many unknowns? Two unknowns. That means, my dear friend, in engineering mechanics, I told you, whenever the number of unknowns are more than the number of equations, number of static equilibrium equations, that you know that we call that type of situation to be indeterminate structure. That type of situation we call indeterminate structure. Insufficient, statically insufficient to determine. That is in short, right? Now tell me from where we can get the second equation. From where we can get second equation? Because you need second equation also. With that one equation, you cannot able to solve it. That is guaranteed. Tell me, guys. Yes? Only one response I got it. Tell me, guys. What will be the second equation? What will be the second equation? What will be the second equation? Yes. At C, what you want to calculate? I don't understand. Total deflection will be 0. Total deformation will be 0. That will be my second equation. Total deformation will be 0. That means, what is the total deformation? Deformation in AB member, deformation in BC member, deformation in CD member, together must be equal to what? All together must be equal to 0. What is the PAB? What is the load that is acting in AB member? As of now, what is the load that is being acting in the AB member as of now? According to our sign convention, plus RAH. Check it out. Do check it out, all of you. I am moving literally very slow so that you can understand each and every concept, right? Try to understand the importance of whatever the work we are doing right now. Whatever the load is acting in the BC member, what will be the load in BC? In BC member, what will be the total load? Plus RAH minus the 200. What is the load that is being acting in the CD member? You take it from left hand side or you take it from right hand side. It's better you just take it out from the what? Left hand side, so that you have the all the forces in terms of what? RAH. What is the meaning of RAH? It's not a 3 term, it's only 1 term. That is what? Horizontal reaction forces at the point A. Now, sorry, RAH minus 200 minus 125. So RAH minus 325, that will be your kilonewton. That will be your kilonewton, my dear friend. Once you got it this one, once you get it this one, what you can further calculate? What are the delta AB? PAB, length is what? 1 meter. Area is what? Same. E is what? Same. Plus delta BC, RAH, or directly I can write, my dear friend, the load value. Directly I can write the load value. What are the PAB? RAH minus 200 into 1 divided by AE plus RAH minus 325 into 1 divided by AE, and that is going to be equal to 0. So from here, what you can calculate? RAH value, calculate and tell me the answer for RAH. Sorry. Just tell me the value of RAH, my dear friend. No. Do check it out. It's a very important. Do check it out. It's a very, very important. First of all, calculate the reaction forces. But here there is a one trick. Just wait. Take the E value and do not take this statement. I will tell you why. Whatever the statement has been mentioned, do not note it down, because there is a separate meaning. This will be your question number 2, and right now you are discussing the question number 1. Suppose that, right? So accordingly, if you just calculate 525 divided by what? 3 kilonewton. Yes or no, guys? This will be your RAH value. Check it out. Check it out. Or you can just calculate, you can just have the, in the same problem, we can have the calculation. In the same problem, we can have the calculation also. Do not worry. Right? Yeah. So RAH is what? 175 kilonewton. Please check it out. RAH is what? 175 kilonewton. Please check it out. All of you, please check it out. Once you calculate RAH from this equation, what will be the RAD value? What will be the RAD value? 150 kilonewton, right? Perfect. Perfect. And that is what you need to calculate. The very first question is what? Very first question is determine the load shared in each portion. Now, once you have the RH value, you can calculate the load in each one, right? What will be the load in AB member? 175. What is the load in BC member? Minus 25. What will be the load in member? CD member. CD member. Tell me, guys. 150 kilonewton, right? Yes or no, guys? Yes or no, guys? Minus 150 kilonewton, right? Perfect. My dear friend, one thing you got to know that, sir, I have not changed the sign of this reaction forces. Why I have not changed the sign of reaction forces? After calculation, I got positive value. After calculation, I got positive value. In fact, that means that whatever the assumed direction is there, that is correct one. Understanding what I was telling before question? Whether it's clear now? Please note it down. Very important. Very, very important. Now they are asking stresses in each member. You can calculate the stress value in AB member. Suppose PAB divided by area AB, right? Through that, you can able to calculate stress in BC member, CD member also, right? But why it is different from the other question? In previous question, there was only one beam, suppose different beams are there, but they have been fixed at one end. Other end, there might be deflection is possible, but right now it is fixed at both the ends, so there will be two reactions, not one reaction. To find the second reaction forces, we need to find from the what? One more equation, that is what? This one. Total deformation must be equal to 0. And this equation we call compatibility equation. I told you, right, in the engineering mechanics, I will discuss this thing in the strength of material. Compatibility equation. Note down, very important. Compatibility equations. Second equation is there, we call compatibility equation. It's not a static equilibrium equation. It is not a static equilibrium equation. It's just a compatibility equation. Remember, many times we will use this equation. Again, we will use in the deflection chapter also. Deflection in the vertical direction because of the hinge support. There also we'll discuss the same thing. Whether it's done, I think done, right, all of you? Remaining question you can solve, my different. There is no worrying thing about this. You need to find the distance through which B and C move. B and C will move. That means simply you need to calculate B with respect to D and C with respect to D. That's it. That's it. You need to calculate, right? All of your understanding? Suppose some of you might be thinking, why you're not calculating, sir, B with respect to A? You can calculate. But you need to calculate with respect to what? Fixed end, not with respect to intermediate member or intermediate points. That you need to remember. And of course, do not forget to take the E value for calculation, that is 80 gigapascal, right? So 80 into 1000, that will become what? Megapascal, right? Now, note on the next concept, thermal stresses and strain. Thermal stresses and strain, one of the important topic, one of the very, very hot topic, we can say that for the actually gate examination. Note down. And what do you mean by the thermal stress? As of now, whatever we have seen, what we call? Whatever the stresses we have seen, sigma, what we call? At a particular member, if any member would have been there, any member is there, and when I apply the load, suppose cross-sectional area is A, then whatever the calculation is there, P by A, this we call mechanical normal stress, right? Understanding, all of you? Suppose this is there at the atmosphere temperature. By somehow I increase the temperature, suppose delta T has been increased. Then whatever somebody will ask you total stress, then total stress will not be equal to sigma. The total stress will be sigma plus sigma thermal. Sigma mechanical plus sigma thermal. That will be the correct answer. In any member, in the whole universe, in the existence, the total nature of the stress in the mechanical component will be mechanical stress plus thermal stress. Please note it down. Put a note and note down. So all of you are understanding? Tell me, guys. Subject is easy. Do not make it very complicated. If you make it complicated, you can solve the previous year question, my dear friend. You can solve the previous year question from this particular chapter. You will be able to solve the question. If not, then there is some problem in actually communication from subject and you, in between the subject and you, right? So try to understand the material as human being only, right? And try to deal with that. Whenever you try to disturb anybody, then definitely that person might be in the what? In the stress condition. The same thing happen in the what? With the material also. So if somebody said that the materials don't have any feeling, that is a wrong thing. As a being an engineer, if somebody will ask you from the engineer point of view, then you must say that is having the feeling. But non-technical person, he will say that it's a immaterial, right? Now, if there's no feeling, then why the mechanical engineers are being hired in the big public basically public service commission, or you can say the PSU, or you can say that private sectors or big organizations, if there is no stress at all, right? So it is a very, very big words. Suppose if I talk about the Boeing, right? So many aerospace industries, what? The main manufacturer dealer is what? Suppose Boeing is there, right? And a lot of development is going on in the suppose aerospace industries. And a lot of Boeing actually is paying what? Lakhs of money per month to the what? Thermal stress engineer, right? Then what is the meaning of those things? If there is no stress, there will not be any engineer, right? But we are seeing by our own eyes. In fact, you are seeing from your campus placement also, the mechanical engineer is being hired, then definitely there has to be one stress value that you can show to the non-technical person who is doing BSc or maybe some other BBA or MBA course, right? Now, done all of you? All of you have noted down? Now, so note down the thermal stress. First of all, note down all the things which are there on the slides. So thermal stress is in the simple bar. If I take only simple bar, we are having the length L. Now let me draw the diagram also. Let me just draw the diagram and let me prove it. So whatever the thermal stress which you are looking right now, this particular formula. So this is the thermal stress, alpha into delta T into E. So whatever the delta T is there, that is increase in temperature or decrease in temperature, it has been written as T only. So please note down this notation also. And every material is having what? Coefficient of thermal expansion, right? Because of that only, because of this alpha only, my dear friend, because of this delta L, in casting, there is a provision of riser. Understanding? Because of this only, my dear friend, we just try to provide the whatever the component is there. Suppose that you are doing the casting, right? Suppose there is a basically what? There is a component is there. This component is there. But whenever if you want to make a rectangular box, suppose, right? If you want to make a rectangular box, if you just exactly taking LBH height, then definitely there might be some contraction, because every material is having what? Every material is having coefficient of linear expansion, and because of, you can see the formula also, delta L into alpha into delta T. If alpha is 0, delta L will be 0. Now delta L can be positive, delta L can be negative, right? Now tell me for which material there is a expansion is there apart from contraction. Every material contract. When we cool it, see, when we cool, delta T will decrease. Upon cooling, delta T will decrease. So delta L will what? Decrease. So that solid contraction will be there, right? there will be solid contraction, and because to overcome this solid contraction, we provide what? Pattern to be oversized. Yes or no, guys? Pattern to be oversized. Am I right? If we provide extra portion to the particularly what rectangular box, now we place it and cool it, having the more gap, even though contraction will be there, I'll be getting exactly perfect size. I'll be getting exactly perfect size. But my friend, due to certain conditions, what happens? Some material, they might show the nature upon cooling, even delta T is decreasing, but they have the expansion. Tell me guys, which material we have? And there is a question also in the gate examination, not one time, two times. Tell me guys, how can you forget that? Whether casting is over or not in the production in section 4. Tell me guys. No, I'm asking you in which material, even though we are cooling, there is a expansion. Suppose that we are cooling any material, there might be expansion. Tell me guys, don't take much time. I'm just waiting. I believe that the casting is over, right? I believe that the casting is over, right? Perfect. Gray cast iron. Don't say iron. Do not say iron, because iron has so many classifications. Gray cast iron, wrought iron, a lot of irons are there, right? Alpha iron, delta iron, gamma iron. Gray cast iron is having so special character. Gray cast iron is having some special feature. Even you cool it, it will try to expand. For that, we need to provide the pattern to be what? Undersize. Right? Please note down. Very important. Right? So whatever the expansion is happening, suppose any material is there, any material. Now, how we got the derivation? That is what I'm showing right now. So can I remove all the part? I think casting part is being done, right? Comfortably, you can understand this thing, right? Yes or no, guys? Please try to revise continuously so that it will be useful. Whatever the lectures has been provided, right? That will be useful. Otherwise, there will not be any use. Suppose there is a material which is having a length L. Now it is being increased by the temperature T. Now it has been increased by the temperature T. This particular component is being fixed at both the ends. Now tell me guys, what will be the total deformations? Zero or not? What will be the total deformation? It is zero or not? Perfect. What will be the reaction forces, my dear friend? What will be the reaction forces? Suppose reaction forces is what? RA here and RB is here. Suppose point A and this is what? Point B. RA is here and RB is what? Suppose here. RA is here and RB is what? Here. Suppose that. Now, yeah, perfect. RA will be equal to what? RB. But the directions will be, opposite. Total deformation means mechanical deformation plus thermal deformation. Together must be equal to what? Zero. Together it must be equal to what? Zero, my dear friend. What will be the mechanical deformation? Can you please tell me? What can be the mechanical deformations? Can you please tell me? Tell me guys, what will be the mechanical deformations? PL divided by A. This is what the formula we have. What will be the load value in this one? What will be the loading value? What will be the load in the member APAB? Can I say minus RB? Can I say minus RB? Can I say minus R? Perfect, my dear friend. So what will be the thermal deformation? Alpha into T into L. Together you can write minus R into L divided by AE plus alpha into T into L. That must be equal to 0. So from here, what you can calculate? Alpha into T into A into E. That will be what? Reaction forces. Once you got the reaction forces, what will be the thermal stress? What will be the thermal stress? Reaction force divided by area. Reaction force divided by area. Alpha T AE divided by A. A will cancel out. Alpha into T into E. Check it out. All of you are getting my point, which I'm saying right now. Check it out. The proof is very important. Without proof, fundamental thing will not be clear. Now, once it is done, please let me know. This is the case number 1. Whatever we are discussing, that is the case number 2. Note down the case number 2. Whatever we are discussing, that is case number 1. Note down the case number 2 from here to here. From here to here. See, each and every sign convention we are using by different. Yes or no, guys? Mechanical deformation will be compressive. Thermal deformation will be what? Expansive. Tensile in nature. Because we are increasing the temperature, it will try to elongate. The moment it will try to elongate, this reaction will say, where actually you are moving. Come back. Come back to the original position. Due to that only, the nature of the stress, mechanical stress will be what? Something like a compressive, but thermal stress will be what? Something like a tensile in nature. Right? So altogether, this will be tensile in nature. As of now, it's a tensile in nature because it's what? Because of temperature effect, it is trying to elongate. Note down, it's a very, very important and very important conclusion, my dear friend. You know that in a particular bar, cross-sectional area A, cross-sectional area 2A, when we apply the load, something like this, tell me which section experience more stress value. Section A, section 1, section 2. Which section is going to experience more stress value? Again, you are saying wrong thing. Why you are not focusing on the formula? See, load divided by area. When area will be less, stress value will be more. Even the load is same. Load is being same. Focus on the area. When area will be less, stress value will be more. In section 2, we have provided large area, large enough area, twice area. How it can able to fail? How the stress will be more in that? The stress will be more in the what? Section 1 only. But my dear friend, thermal stress is independent of the dimension of the member. Note down important point. Thermal stress. I'm talking about the mechanical stress. These all the discussions are happening for mechanical stress. Thermal stress is independent of the anywhere in the formula you are saying area or length, nothing, right? Thermal stress is independent of the dimension of the member. Important point. Put a note and note down. Once it is done, let me know. We can discuss about the case 2. And I'll be asking you so many questions based on thermal stress. So have patience. Done, all of you? Is it done? Perfect. Perfect. Now, let me add just one slide. I just need only one slide. Yes, now it's fine. The case 2, the partial restriction. So whatever the case 1 is there, we can call complete restriction. You can note down complete restriction. This, whatever the support you are looking right now, this is a complete rigid support. Complete restriction is there. But case 2 right now we are discussing, that is a partially restricted expansion. In one direction. So whatever the formula you have noted down for the case 2, right now we are discussing the proof for that. Now, again, look at very carefully. Suppose there is a member. Suppose there is a member. Now there might be, reaction forces will be there. Definitely there is a reaction force. But this particular support is what? Not a very rigid support. It's a flexible support. Suppose that. It's a flexible support. Because the moment you increase the temperature, it will try to elongate. It will try to elongate. The moment you try to increase the temperature, it will try to elongate. There is no doubt about it. But this reaction forces will not be able to compress it up to this particular thing. Maybe it will able to compress up to this. So how much of expansion it is allowing? Suppose lambda. Understanding what I'm saying? Expansion allowed will be only lambda only. In before case, lambda was 0. In before case, there was no expansion allowed. Complete 0 expansion was there, right? That's why we are equating delta total deformation to be what? 0, I define. Now, what again we are doing? Total deformation right now is not 0, it's a lambda. Am I right? Whatever the compatibility equation is there, the total deformation will not be 0. Total deformation will be lambda. I'm moving very slowly so that you can develop some fundamental understanding. Right? In BTech, generally the question has not been asked a very good level in the university level paper. That's the reason we do the actually do not have the very strong in fundamentals. That's the reason I'm discussing very slowly so that you can have the fundamental. Once we have the fundamental, we can play with the subject. Now, total deformation means mechanical deformation plus thermal deformation. Just note down the up to this part I will discuss. What will be the mechanical deformation, my dear friend? What will be the mechanical deformation? You know that. Minus R into L. Suppose length is what? L. L into A divided by E. What will be the thermal deformation? Alpha into T into L. So minus R into L divided by AE. Alpha into T into L. That is equal to what? Lambda. That is equal to what? Lambda. What is this? R by A. Directly I am writing what? Sigma. Sigma thermal. I am calling this to be sigma only. So minus sigma L divided by E plus alpha TL, that is equal to lambda. Then what will be sigma value? What will be the sigma value? Alpha TL minus lambda into E by L. Check it out. Please check it out. Are you getting the same formula? Right? Note down. Very important. Note down. It is positive when temperature increased, negative when temperature decreased. Very important. Is it done? Is it done, all of you? Different cross section. Now they are being connected from fixed end like this. What we can say, it's a series connection or not? In series connection or not? Perfect. Whenever they are connected in series, total deformation must be 0. That means mechanical deformation in member AB, thermal deformation in member AB, mechanical deformation in member CD, in BC, plus thermal deformation in member, BC. All together must be 0. Start telling me the value. Start telling me the values. Reaction forces will be equal. Yes or no, guys? Reaction forces will be equal. What will be the mechanical deformation? Minus R into L1 divided by, suppose area is what? A1, and here is area is what? A2. A1, E1. What will be the thermal deformation? Now suppose that temperature has been increased, my dear friend. Alpha 1. This component is having coefficient of thermal expansion alpha 1. This is having alpha 2. Alpha 1 T into L1. What will be the mechanical deformation, my dear friend? Minus R into L2 divided by A2 into E2. Right? Plus what will be the thermal deformation, my dear friend? Alpha into alpha 2 into T into L2. All together must be equal to 0, my dear friend. What about this thing? Sigma 1. What about this thing? Sigma 2. Sigma 1 and sigma 2 is nothing but thermal stresses in member 1 and 2 respectively. Yes or no, guys? So sigma 1 L1 divided by E1 plus sigma 2 L2 divided by E2, that will be equal to alpha 1 T into L1, alpha 2 into T into L2. Yes or no, guys? That will be your final equation. Note down. So this is the first equation. Suppose we want to calculate sigma 1 and sigma 2. So this is my first equation. What can be the second equation? Can anybody tell me? What can be the second equation? Very important. Reaction forces R1 equal to R2 equal to R. What is the reaction forces? Sigma 1 into A1, sigma 2 into A2. Understanding what I'm saying? That will be my second equation. Two equation, two unknown. You can able to solve what? Sigma 1 and 2 in the bars, right? Understanding what I'm saying? Perfect. Very important. Now some of you might be thinking, sir, you are telling load by area as a mechanical only, but right now also there is no different load by area only, you are taking thermal. Remember, there was no external load. Any load is there in the member? Tell me, guys, any load is there? Any load is there in the member? External load, I'm talking about the external load. P, P2, 2P, 3P, 5P, 6P, nothing is there. If nothing is there, sigma mechanical will be 0. When the temperature has been increased, then there is a thermal load is being imposed. And because to resist the thermal load, there must be thermal reaction must be coming. Thermal reaction, thermal stress will be coming. Understanding or not? All of you. All of you are able to follow me? Yes, very important. Very, very important. Put it in the box. Again, I'm saying things are very simple. Do not make it very complicated by learning things from other sources or very low standard textbook. Do not follow RS Kurmi, first of all. If you follow RS Kurmi, lot of conceptual mistake in the solving in numerical also, and everything. For every subject, do not follow. Even each and every subject must be avoided if you follow RS Kurmi. RS Kurmi should be avoided completely. You should only follow RS Kurmi when you are preparing for objective question. That's it. That too, there are a lot of mistake actually, but you need to stick to the concept. Then you just believe in the concept and try to put the answer according to you, not according to RS Kurmi. Now, then all of you. Shall we discuss about the parallel combination? Shall we discuss about the parallel combination, all of you? Yes. Perfect. Now done thermal stresses in the composite bar. Composite bar means compound bars. How you can identify the members are connected in compound or something like that? Whenever the two member is being connected like this, side by side, member one, member two. It is a heading of, means it's a just the basically resembling the compound bars, or maybe it may be connected like this. Member one, inside that we have just inserted another member one, and this is my second member. Member one is being connected inside the second member. So either like this or like this. Whenever the two situations will be coming, both the situations resemble the composite bar, compound bar, parallel connections. Note down. Now, once it is done, let me know when the diagram is being over. Suppose for member one, there is alpha 1 and alpha 2 is there. And suppose alpha 1 is more than alpha 2. When alpha 1 is more than alpha 2, then thermal expansion will be more. When the moment you increase the temperature, thermal expansion will be more in member 1 as compared to the member 2. Thermal expansion will be more in member 1 as compared to the member 2. There is no doubt about it. There is no doubt. There is no doubt about it. Yes or no, guys? Member 1 will expand more as compared to the member 2. Right? Now, what will be the deformation? What is the boundary condition? I said delta 1 equal to delta 2. Total deformation in member 1 equal to total deformation in member 2. Yes or no, guys? Total deformation in member 1 must be equal to total deformation in member 2. Am I right? Perfect. Sir, what is the deformation in member 1? Suppose member in 1 is what? Alpha 1. That means which is having a more thermal expansion. Then what would have been the conditions? The member 1 will try to expand like anything. Let me draw the diagram. The things will be clarified after that. This is the member 1. Sorry. And this is the member 2. Member 1, member 2. Now member 1 is being elongated like this. Member 1 is being elongated like this, where the temperature has been increased. But member 2 is being elongated up to this only. Suppose that. Now reaction forces will be coming. Reaction forces will be coming. And what the reaction forces will do? Come back to the original position. But they will not be able to bring back this to the original condition. Suppose the final position is somewhere here. The final position is what? Somewhere here. Both the reaction forces, they were able to bring the conditions what? To this particular conditions. Now tell me, what will be the nature of the stress in component 1 and in component 2? What will be the total deformation? Mechanical deformation in member 1 and thermal deformation in member 1. Start telling me the value of mechanical deformation. Minus reaction forces or plus reaction forces? to bring this body to this final position, it has to compress or it has to elongate. It has to compress or it has to elongate, my dear friend. And of course, reaction forces are same. Here also the reaction forces are must same. There's no doubt about it. Reaction forces, suppose that it is being fixed at one end. Suppose it is being fixed at one end. Whatever the reaction forces will be there, reaction forces must be equal. There's no doubt about it. Because there's no load, it has to be equal. Now, but the nature of the reaction forces must be different. In the mechanical, first one will be what? Minus of R into L divided by what? A1 E1. Understanding what I'm saying? Length is same. Suppose length is same for both the member. Length is same. That is what so special characteristic about the parallel combination. But thermal deformation is what? Alpha 1 T into L1. Am I right? Perfect. But what is the total deformation in second member? There is a mechanical deformation, sir. And there is a thermal deformation, sir. Sir, what is the mechanical deformation? What will be the nature to bring back this particular body to original conditions? It has to apply tensile force. Check it out. Check it out. Check it out. It has to apply the tensile force. Do check it out. Perfect. Perfect. Now you try to equate. Now if you just try to equate, what you can calculate? R by A1 sigma 1, R by A2 sigma 2. When you just equate total deformation equal to total deformation, when you rearrange the terms, you will be getting, my different. You will be getting the answer as sigma 1 L1 divided by E1 plus sigma 2 L2 divided by E2. That must be equal to alpha 1 minus alpha 2 T into L. And of course, L1 is same as L2. L1 is same as L2. So this will cancel out. So what you can calculate? Sigma 1 divided by E1 plus sigma 2 divided by E2 will be equal to alpha 1 minus alpha 2 into T. That is the first equation. And from here you can calculate second equation. By both the things you can calculate two equation, two unknown. Nobody in the whole universe will able to stop you to calculate sigma 1 and sigma 2. Understanding the difference between series connection and parallel connection? All of you. Understanding the difference between series connection and parallel connections? Check it out. Very important, very interesting. Now some of you may not be able to digest, sir. The final position will not be here. Final position may be here, may be here. But believe me, that will be the final position. One member will elongate like anything, but one member will not be able to elongate. On an average, mathematical analysis, if you just apply, it will be coming to here. Right? There will be some deformation. It is not just like a series connection where the deformation is zero. There will be some deformation from this to this. And that deformation, that particular deformation will be equal in both the member, total deformation. But for bring back first body to this position, it has to apply compressive force, and second body, it has to apply some tensile force. That is what the small difference is there. So note down. In ISRO, multiple times it has been asked. ISRO 2015, one question is there. Similar question has been there. Composite bar is given, and they said that when temperature is decreased, alpha 1 is more than alpha 2, then what will be the nature of the stress in member 1 and member 2? Note down the question. And and tell me the answer. What will be the nature of the stress in member 1 and member 2 when temperature will decrease? This condition we have seen when temperature has been increased. When temperature has been increased, my dear friend, you know that the member 1 under compressive. Yes or no, guys? Member 1 was under compression. Am I right? All of you, please check it out. Member 1 was under compression and member 2 under tension. But similarly, condition will be there when the temperature is being decreased. In this case, member 1 will be tension. Member 2 will be what? Compression. Understanding or not? All of you are understanding? In the series connection, my dear friend, whenever the stress value will increase, both the member will be what? Under compression only. Member 1 and member 2 will be under compression. Understanding? Member 1 and member 2 both will be under compression only. You can check it out. Minus R by A, sigma 1. Minus R by A2, sigma 2. Yes or no, guys? Understanding what actually I'm talking about? Tell me, guys. The nature of the stress will not depend whether it is expanding due to thermally or contracting because of temperature. No, no, no. It depends on the nature of the reaction forces, whether it's a positive or negative. That's it. Right? I know that it's a very difficult to digest from the very first instant, but when you keep on practicing and when you keep on applying the logic, when you keep learning the things, it will be able to you will be able to digest after some point of time, right? Because this is what this strength of material. It's very different from other subjects, right? Lot of sign convention, lot of things are there that is unusual actually as compared to the other subject. Other subject straightforward is there, but thing is not same over here. And based on this thing only, whatever you are learning right now, maximum subjects are dependent on this thing only. Strength of material only. Or your machine design, your metal forming, all that, whatever the calculation is there, whatever the formulas are there, strain value, true strain, engineering strain, all will depend on this particular strength of material. Is it done, all of you? So put it in the highlighted box. It is a very important. This thing, I'm talking about this thing. Done? Shall we solve the numerical? Hooke's law valid up to proportional limit. Understanding or not? If in the option elastic limit is there and E option is proportional limit is there, right answer is proportional limit, not elastic limit. Understanding? All of you are understanding? It's a valid only for what? It's valid only for what? Valid for linear elastic material. So whatever you can grab it, you please try to grab it. Sigma and epsilon, it has to be linear one. Right? Whatever the E value is there, slope of what will be the slope of sigma stress and strain diagram? What will be the slope of stress strain diagram? What will be the stress of slope of stress strain diagram? What is the slope? Delta sigma by delta epsilon. Tell me, guys, do not delay. If you just keep on telling very fastly so that we can discuss more number of concepts, more number of problems in the class itself. Yes. Tell me, guys. Come on. What will be the answer? Young's modulus. Young's modulus. Note down, very important. Very, 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 very important. Done, all of you? Is it done? Now, Let me ask you one more question. Whether Hooke's law is valid. Sorry. Whether Hooke's law is valid for rubber. Rubber is also one of the elastic member. Whether Hooke's law is valid for rubber. A very general question I'm asking you. For steel, it is valid. For steel, it is valid because we have seen that there is a linear momentum is there initially. There is some linear curvature is there that we can able to understand that there is a it's a linear elastic material. Linearly elastic material. So Hooke's law is valid, right? But I'm asking you for rubber. Tell me. Any one of you. Rubber is also one of the elastic member. So for elastic material, you might assume that the Hooke's law may be valid, may not be valid. What will be the final answer? Quickly, guys, quickly. Today we need to finish first chapter completely. It is not going to valid. When you see the rubber, it is something like this. When you see the stress strain diagram, it's a non-linear one. Maybe it is varying parabolically kind of thing. Non-linear. It is elastic. It is an elastic member. It is elastic material. There's no doubt, but it's a non-linear. Non-linear elastic material. So that's the reason. Hooke's law will say, sorry, will not valid. Note down, very important. So what will be the answer? A big no. Is it clear? All of you are understanding my point? Yeah. Perfect. Done. Can I move to the next thing? Of course, rubber is, we have the two types, soft rubber and hard rubber. Hard rubber is behaving like a rigid body, or maybe it's just behaving like a brittle material. So brittle material, you know the graph, right? Now, try to solve this question. Try to solve this particular question and tell me the answer. Take your time, take 2 to 3 minutes of time and try to tell me the answer. At least we need to finish first chapter today, along with the elastic constant. We have the 4 elastic constant: E, G, K, mu. Till now you have seen only one elastic constant, E, and just slightly you have seen the Poisson ratio. That is 2 types. Another 2 types is also there: bulk modulus and modulus of rigidity. Modulus of rigidity we also call Shear Modulus. Now, in tomorrow's lecture, morning we have the lecture. We will try to finish tomorrow. Very important class. Shear force, bending moment diagram. Those who are having doubts, you might have a lot of doubts. Single doubt will not be there after the class, right? That is my challenge. So tomorrow we are going to learn shear force and bending moment diagram. That is the 3rd lecture. 4th lecture we are combined together. We will learn bending stress and shear stress. That is our 4th lecture. 5th lecture will be we will try to cover, thin cylinder and thick cylinder, and we will try to solve the numerical so that we can have the idea. Sixth lecture, we are going to have, principal stress and strain. Then seventh lecture, we are going to completely dedicated to what? The strain energy and deflection chapters, right? Understanding all of you? And the eighth chapter will be columns, right? Understanding or not, all of you? So we have allotted 8 particular lectures for this form, right? So we'll try our level best to finish particularly, this particular beautiful course. Now, anyone got the answer? Let me, quickly know about this thing without any further delay. It's a very simple, just whatever the formula we have seen, based on that only the things are there. Not that much difficult. Rails are laid such that there will be no stress in them at 24 degrees centigrade. When the temperature is 24 degrees centigrade, there is no stress. The moment, and the length is 32 meter, the moment you increase the temperature, that is final temperature is what? 80 degrees centigrade. How much of increment is there? 80 minus 24. What will be the value? If you just increase the temperature, my dear friend, then thermal stress will be there. And simply they are asking thermal stress only. Simply they are asking, my dear friend, thermal stress only. And there is a, this is our case number 2 that we have discussed. There is some expansion is being provided. That means that much of elongation. Actually, this is supposed to be fixed support, but the fixed support has been flexible enough so that it is providing the allowances of 8 mm, my dear friend, right? So that it is providing the allowance of 8 mm. And now we need to calculate, thermal stress that we can calculate directly from the formula. Nobody is telling me the answer, guys. I was just waiting. Alpha, you know that. T, you know that. 80 minus 24. What is the answer? 80 minus 24, 56. L. L is what? 32 into 1000. So that it will be converted in mm. Minus 8 mm into E. What is the E value? Newton per mm square into 1000 divided by L. 32 into 1000. Try to calculate and let me know the answer. You will be getting as 75 megapascal. Right? And what will be the nature? Compressive. Understanding or not, all of you? Any doubt? They clearly mentioned that the expansion allowances has been given. That means it is our case 2. All of you are understanding or not? Perfect. Shall we discuss next one? Done? Now, try to solve this one. Do not worry. First of all, Be calm, composed. Try to digest this numerical. This has been asked in engineering sources. That means there will not be any calculator allowed. So similarly, relevancy will be there in nature examination also. Try to see, then answer. Because if I start telling you the solution, you will not be able to apply the logic, my dear friend. Right? It is just like a mugging up the things. That is not good actually. So please try to stick to the whatever the concept has been discussed. Try to stick with that. Rigid beam. I just told you the meaning of rigid also. That is the engineering mechanics part of thing. Negligible weight. That means self weight is being neglected. There is a two rod. One is a steel. Another is what? Aluminium. Length is given. Area has been given. They are asking the rigid beam is to be remain in horizontal. Right? If the rigid beam remains to be what? Horizontal, my dear friend. Remains to be horizontal. Then you can see the conditions. Then you can see the condition they are asking. Very, very simple question. Look very tough, but very easy. This question must not be able to, given that much time. Tell me, guys. Any answers? See, whenever they are saying that the rigid bar has to remain in the horizontal condition, that means there is a deformation in both the rods automatically. Automatically, we'll say. Otherwise, what will happen? If the deformation will be different, this is the rod, suppose. If suppose deflection is different, then what will happen? Suppose it is deforming like this. Then what will happen? The deflection might be different. Of course, the deflection might not be something like this. Let me show. Here delta 1, here delta 2. The things will be different. Delta steel, delta aluminum will be different, but they have clearly mentioned in the particularly paper, if the rigid beam remains to be horizontal, and definitely because of the loading condition, the some amount of deformation will be there because it is not fixed one. The rod is being connected with this one. So definitely there might be some deformation, right? And but because of that deformation, this particular beam is what? Remains in the horizontal condition. So delta of steel will be what? Delta of aluminium. Delta of steel will be what? Delta of aluminium. Now what about delta of steel? P steel, L steel, A steel, E steel. Delta aluminium, P aluminium, L aluminium, E aluminium, A aluminium. Try to equate. Try to equate. And let's see what we are able to get it. Let's see what we are able to get it. LS value is what? 2. L aluminum is what? 1. Surface area, cross-sectional area is being given for the steel is what? 100 mm square. And for this one, they have given 200 mm square. What else they have given? E of steel, they have given 200 gigapascal. For this, they have given 100 gigapascal. Put the value, get the answer. Put the value, get the answer. Check it out. It's a parallel combination. It's a compound bar. Check it out. All of you, please check it out. All of your understanding? Is it done, all of you? So forces in the aluminum bar will be twice the steel rod. Now, moving on to the next segment. All of you have noted down, right? All of you have noted down, right? Yes. Perfect. Perfect. Now, note on the next topic, elastic constant. Note on the next topic, elastic constants. Elastic constant, very important. In fact, this will be the last topic for the first chapter. First chapter is somewhat big one. Elastic constants. Now, not only Poisson ratio, you know that Poisson ratio. It's a ratio of the lateral strain to the linear strain. Lateral strain to the linear strain. We also say lateral strain to longitudinal strain. Lateral strain to longitudinal strain. Done, all of you? Is it done? Perfect. What is happening? Yes. No doubt. The volumetric strain of a rectangular body, volumetric strain of a rectangular body is subjected to three mutually perpendicular forces. When the forces are applying only in the one direction, then we have seen the volumetric strain, right? Yes or no, guys? We have seen the volumetric strain, right? Tell me, guys. When the forces is being applied in one direction, we have seen the volumetric strain for the cylindrical bar as well as we have seen for the cubical element. When the rectangular box is being supplied to what? Three forces in the horizontal direction, sigma x, sigma z, and sigma y. Suppose that under these three stress condition, my dear friend, we need to find the volumetric strain. First of all, tell me, what will be the total strain in x direction? Because of the load in x direction, there will be strain in x direction, right? Sigma x upon E, right? Check it out. Sigma x upon E, right? Tell me, guys. Forget about the other loading conditions. Forget about the other loading condition. Just focus on the one load. When I apply the load like this, when I apply the load, sigma stress will be acting in this material. Because of that, there is a, some extension will be there. But in other direction, there is a compression. So what will be the longitudinal strain? Sigma x upon E, sigma x upon E. But what about the lateral strain? Tell me. What will be the lateral strain in this direction, in the y direction? Tell me, guys. Minus mu into sigma x upon E. Yes or no? Minus mu into sigma x upon E. Yes or no, guys? Check it out, check it out. Perfect. Similarly, when we apply the load in the y direction, then there is a something elongation will happen like this. But because of that, there is a some lateral compression will be there. How to calculate lateral strain for this case? Minus mu into sigma y upon E. Similarly, when we just load it in the z direction, again there is a some kind of compression might happen, and because of that the lateral strain can be calculated as minus mu into sigma z upon E. I'm asking you total strain in x direction. What will be the answer? Sir, this one plus this one plus, sir, this one. Check it out. Not believing? Compression, compression, tension. Together effect will be called as total strain in x direction because load has been applied in three directions, x, y, z. In before cases, we have applied the load in only one direction. Understanding or not? All of you are understanding? Perfect, fine. Perfect, fine. Now, what will be the total strain in y direction? Sigma y upon E minus mu into sigma x upon E minus mu into sigma z upon E. Similarly, total strain in z direction will be sigma z upon E minus mu into sigma x upon E minus mu into sigma y upon E. This will be the formula, my dear friend. This will be formula, my dear friend. This will be formula, my dear friend. All of you are understanding my point? All of you are understanding my point? But this particular formula, whatever the formula you're looking right now, this is going to be valid. This is all the formula will be valid. Note down one important caution point. Valid when sigma x, sigma y, sigma z is positive. The moment any value will be compressive, it will be what? Sign will be changes, right? Note down, very important. Note down this point. Many of you, in fact, 99% public used to forget this thing. They know the formula, but they forget this thing. Please note down. Under which condition it is valid? Under this condition. Now, once it is done, then let me know. Done, all of you? Is it done? Yes. Perfect. Perfect. So total volumetric strain will be sigma x, sorry, epsilon x, epsilon y, epsilon z. Please note down. And you know that individual formula. Do not worry, 1 upon m is also said to be mu only. Right? What upon mu? Mu, it's a Poisson ratio. Very, very, very important. For which of the casting material we do not provide the pattern allowances at all? We do not provide sinkage allowances, rather to say. For grey cast iron, we provide positive allowances. Other than that, negative allowances. For other than that material, steel, aluminum, for all material, we provide positive allowances. That means we provide pattern size to be what? Larger in size. Now tell me for which material we provide zero sinkage allowances. Yes, try to think and tell. Try to think and tell. Done, all of you? Is it done? Note down the bulk modulus. Note down the bulk modulus. It is defined as the ratio of direct stress to the volumetric strain. It is defined as direct stress to the volumetric strain. It is also one of the elastic constant. Somebody will ask you how many types of elastic constant we do have. Elastic constant we do have. Then what you will say? E, G, K, mu. E is what? Young's modulus. G is modulus of rigidity. K is bulk modulus. Mu is Poisson ratio. Note down, very important. When a body is subjected to three mutually perpendicular stresses of equal intensity, the ratio of direct stress to the corresponding volumetric strain is said to be bulk modulus. You will understand the bulk modulus in fluid also, fluid mechanics also. Volumetric strain is 0 for what? Water. That's the reason K is what? Infinite. The ratio of, the inversely proportional, the inverse of K is called to be what? The inverse of K is called to be what? Tell me, guys. Compressibility. The inverse of K, or the inverse of the bulk modulus, we say 1 upon bulk modulus, we say it's a compressibility. Water we cannot compress, so it's incompressible. Compressibility will be 0 for this case water, for this particular water. Note down, very, very important. Done? Tell me, guys, done? Perfect. Note down the shear stress. Okay, we'll discuss about after that. Yeah. Note down G value. Because in the bending stress and shear stress, again, I need to discuss about the shear stress. So do not worry. Note down shear modulus, we also call modulus of rigidity. We denote it by G. It has been experimentally found that within the elastic limit, that is according to Hooke's law, shear stress is directly proportional to shear strain. Just like normal stress is directly proportional to linear strain, here also we have, whenever the any load is acting parallel to the cross section, then we are finding shear stress, not normal stress. Suppose this will be the cross section and the load has been applied parallelly, then what will be the scenario? We need to find the normal, shear stress rather than normal stress. So tau will be equal to what? G, right? So tau will be equal to what? G into phi. We will discuss about phi, that what is the shear strain in detail while discussing the principal strain, right? In fact, it will come once again in torsional chapter also. Again, it will come in the what? Torsional chapter also. Done, all of you? Is it done? Now, note down, some of you might be curious to know about the shear strain. Initially, whatever the, this is the particular rectangular bar or square bar. When any amount of load has been there applied, when any angular deformation is there with respect to initial position, that deformation we call shear strain. We also call shear deformation. We also call shear deformation. That is deformation by original length. How much of deformation has been happened? By original length. So according to, you just calculate time 10 phi. So delta divided by L. When phi is very, very small, 10 phi will become what? Phi only. Very important. You can also calculate initial angle between two perpendicular lines minus final angle between two perpendicular lines, two lines. What is the initial angle between two lines, AD and AB? 90 degree. What is the final angle between this line, AD1 and AB? 90 minus 5, yes or no? So this will cancel out. You will be calculating as what? Phi only, right? Now it's now it is coming very easy. But if I say the member is being distorted angularly like this, suppose if I am saying the angle is being deformated, the member is being deformated, something like this. This is what we have alpha. This is what beta. Now tell me what will be the shear strain. Shear strain we also represent it by gamma xy of phi. Tell me guys, what will be the, suppose this is a question and I'm asking you, what will be the, what will be the shear strain in the member? The member is being distorted like this. Now it's very difficult to tell, right? But if you just follow this particular definition, initial angle between this line and this line, 90 degree, minus what will be the final angle between these two lines? 90 minus alpha plus beta. 90 minus alpha plus beta. So what will be the answer? Alpha plus beta. Understanding? All of you are understanding? See, when we have the linear deformation, when we apply the load, that is what we are calculating, PL divided by AE. Similarly, when we apply the load parallel to the cross section, we have angular deformation, shear deformation. We also got angular deformation like this. So that's all for the first chapter. Tomorrow, when we come back in the morning, then we will see shear force and bending moment diagram, right? Done, all of you? Those who have not completed, please note it down. And once it is done, then we can leave for the day. Over. I think, yeah. Thank you all. I hope that you enjoy the session. Try to use the this concept and try to solve as many as problem. Take any book and try to solve. If not, then there might be some problem. I know that some of the questions cannot be solved. That particular thing, no, in particular GATE course, we are actually solving exhaustively all the particular problem from BC pneumonia and Thymosin and Gere. A lot of problems will be covered in the class itself. There you will get a lot of confidence actually, right? But here we cannot discuss all the problem because you know that we don't have an calculator is also not allowed. So again, relevancy will also be not made if I just take any difficult problem, right? Okay, guys, thank you. Yeah.